Okay, so welcome back. What we saw in the last lecture was how to generate residue curve maps, residue curves using a rigorous model, thermodynamic model, either Raoult's law, if it was a simple system, ideal system, or NRTL. I had asked you to do that as a homework for 3 different cases. And we saw a little bit about how do we make use and what kind of things are what kind of information that we get out of these residue curve maps. Very briefly we saw it. We will see this in more detail in the coming lectures. In this lecture, what we are going to do is to look at how do I generate an approximate residue curve map. I can do a rigorous calculation and generate an actual realistic residue curve map, but if I don't want to do that, at least an approximate, how much can I get an approximate idea of how the residue curve maps will look like, whether distillation boundaries will be there, not there, how many distillation boundaries will be there, how many distillation regions will be there. If I can get an idea about that without actually generating the residue curve map by rigorous thermodynamic calculation, it will help me to understand, to visualize the system and how I'm going to do the distillation. So let's get started with our topic now. What we are going to do is to generate an approximate residue curve map without doing calculations, just trying to look at the boiling points and trying to look at the binary data and so on. So let me take an example. So for example, we have 3 components: methyl acetate, methanol, and hexane, N-hexane. So their boiling points are given. So N-hexane boiling point is 69 degrees centigrade. Methanol boiling point, let's say 64.7 degrees centigrade. Methyl acetate is 57 degrees centigrade. Let's look at the binary azeotrope. Now, hexane methanol, there is a binary azeotrope which has a boiling point of 50.6 degrees centigrade. Can you tell me whether it's a minimum boiling or a maximum boiling? Pause, tell me. It's a minimum boiling, hexane and methanol. Look at hexane and methanol, 69 and 64. The boiling temperature is lower of the azeotrope than the individual component, so it's a minimum boiling. What about hexane and methyl acetate? There is an azeotrope at 51.8 degrees centigrade with this composition. It's a again minimum boiling azeotrope. Methanol methyl acetate, again it's a minimum boiling azeotrope. The azeotrope temperature is lower than the individual components. There is a ternary azeotrope of hexane methanol methyl acetate having a boiling point of 47.4 degrees, having this composition. This temperature is lower than all the individual components. Okay, so we are going to generate an approximate residue curve map. We are going to see how to generate an approximate residue curve map for this particular situation. So I'm going to tell you a stepwise procedure. Just follow with me, stop the video, do it for yourself at different periods of time, and then you will be able to understand. First step is to identify pure components in their order of volatility and to draw them on a ternary diagram. So, and draw on a ternary diagram. And it's a good point, it's a good ternary diagram, and it's a good idea to write the temperatures as well of the corresponding boiling points on the ternary diagram itself. So the first step would be to draw the ternary diagram. Let's say we are drawing it like this: methyl acetate here, hexane here, methanol here. So the vertical axis, the y-axis, is the binary of methanol and hexane. The x-axis is the binary system of hexane and methyl acetate. The side of the triangle, hypotenuse if you like, is a binary of methanol and methyl acetate. Okay, and I'm going to write the temperature as well: 57 for methyl acetate, 69 for hexane, and 64.7 for methanol. By writing the temperature, it becomes easy to visualize which is more volatile, which is less volatile. So if I write these temperatures, it's easy to visualize that methyl acetate is more volatile than methanol, and hexane is the least volatile of the 3. Okay, so that's the step number 1. Step number 2 is to locate azeotropes and their boiling points and write temperatures. Okay, pause the video, do it for yourself. Only when you've done, you can continue the video and see whether your answer is matching or not matching. It's straightforward. So binary between methyl acetate and hexane, the minimum boiling azeotrope is 51.8. Hexane and methyl acetate. Let's go back to the data. Hexane and methyl acetate. This minimum boiling azeotrope, it's at a composition of 35.8 mole percent of hexane, 64.2 mole percent of methyl acetate. Here it's closer to methyl acetate vortex than the hexane axis, 35 and 65. That's approximately the proportion. The 50.6 methanol hexane azeotrope, here 50.6, roughly equal mole fraction, 49:51. So let's say 0.5 or 0.49, 0.51. It's easy to draw for us, approximately midway between the two. Next, methanol and methyl acetate, 53.5. Methanol and methyl acetate, 53.5. Composition is 35.2 mole percent of methanol, 64.8 mole percent of methyl acetate, roughly 35-65 if you want. So it is closer to methyl acetate vertex here. Okay. Ternary azeotrope, 47.4. It has approximately, not approximately, exactly 37.2 mole percent hexane, 30.1 mole percent methanol, and 32.7 mole percent methyl acetate. So if you just want to say 0.3, 0.3, 0.0, 0.33, 0.33, 0.33, 0.4, 0.3, 0.3, something like that. So here, this is our azeotrope. Pause the video if you have not done and if you have not got up to this point. So pause and do it for yourself. Make sure that you are getting up to here and you are able to understand everything up to here. Third step now. Third step is to draw the residue curves for binary pairs. Okay, pause and do for yourself. Pause and do for yourself and then only check. So if you look at the binary pair of hexane methyl acetate, there is a minimum boiling azeotrope, so the residue curves will point away from the minimum boiling towards the two vertices. Again, the hypotenuse, the minimum boiling azeotrope, so residue curves will point away from the azeotrope. The vertical axis, minimum boiling azeotrope, so the residue curves will point away from the minimum boiling azeotrope towards each of these vertices or each of these vertexes, each of these pure component points. Okay, pause, do it for yourself, and now go forward. Next step is to consider various compositions from the lowest temperatures and then draw curve corresponding to where the composition will change. We are not going to look at we are not going to calculate the composition. So the only indication available to us is to look at the temperature. So we'll start with the lowest temperature and go towards respectively higher and higher temperatures. Okay. So what I'm trying to say is now we will take different points around this minimum boiling point. Minimum boiling point is 47.4 out of all these 6 points. So we have 3 pure components. We have 3 binary azeotropes, and we have 1 ternary azeotrope. Totally 7 points are there. Correspondingly, 7 ternary azeotrope. Total 7 points are there. Correspondingly, there are 7 boiling points. So I want you to start with the lowest boiling point. Lowest boiling point means what? Most volatile. Most volatile in this particular case is the ternary azeotrope. The least volatile in this case is hexane. So identify order of volatility. Okay, so if you want to identify order of volatility, starting from highest volatile or most volatile to lowest volatile. If you want to go in this order of volatility, the ternary azeotrope is the highest volatile, isn't it? Has the highest volatility out of these 7 points. After that, what is the most volatile? After the ternary azeotrope, then it's a binary azeotrope. between methanol and hexane. That is this 50.7. So if you want, we can identify points. Let's say point number 1 is the most volatile, point number 2 is the next next less volatile. After that, point number 3, that's the next less volatile. Point number 4, that's the next less volatile. So next volatile in this order is the binary azeotrope between, I'm just writing A for azeotrope, between hexane and methyl acetate, and hexane. Next is the binary azeotrope between methanol and methyl acetate. Okay. Next, most volatile, or next lesser volatile, I should say, pure methyl acetate. So that's, we can call this as point number 5 if you like. Next, it is methanol, point number 6 if you like, and hexane, point number 7. Pure methanol and pure hexane. So 1, 2, 3, 4, 5, 6, 7. Now we are going to start with the lowest temperature. Lowest temperature means most volatile, and we are going to take different points around this this most volatile component, the least temperature component, and try to see in what direction would our temperatures go. Okay, do this for yourself. So if you start, for example, from here, for example, you see where the temperatures would go. Let's say you start from here. Where would temperature go? From 47, the temperature will go to the next higher, and then next higher, and so on. Okay, so try to draw it for yourself, and then pause the video, try to draw it for yourself, and then only go forward. Okay, so suppose I take the point here. Now in this direction, what is the next temperature? 51.8, isn't it? In this direction, the next temperature is 51.8. So the residue curve will go towards 51.8. But when it goes towards 51.8, is it going to end in 51.8? No, it's going to go towards the hexane and end there. It cannot go up because the residue curve is pointing away from the upward direction. It's going to point towards hexane. So it is going to end up here. Right? Do you agree with that? Pause, see for yourself, understand for yourself, and then do. Right. Next, take the next point. Say suppose I take the next point here. Now it is in this direction. So the residue curve will go towards a higher temperature than 47.4 in this direction. What is the direction? It is going towards 50.6. But when it goes towards 50.6, if the if we are ending up with a composition lower than 50.6, it will go and turn towards this hexane. Pause, stop, do for yourself, and understand for yourself. That's how this will look like. Next, suppose I take a point here. Now it is in this direction. So we go in this direction from 47.4. It will go towards 51.8. But if we end up on the other side of the azeotrope, other side of this 51.8, where is the residue curve pointing to? It will go towards this methyl acetate. It cannot turn because now the residue curve is pointing towards this vertex. So it will end here at the pure methyl acetate. Pause, do it for yourself. Right, that's how it's going to look like. Next, take one more point. Now in this direction, it will go towards 53.5. But when it goes towards 53.5, if we are on the lower side in terms of composition of 53.5, then it will follow the residue curve direction of the binary. It will go towards methyl acetate. Pause, think, do it for yourself. Only if you agree, then only go forward. Next, take point like this. Now in this direction again, towards 50.6. But now if you end up with the other side of 50.6, it will go towards methanol. From methanol, it cannot turn down because the residue curve for the binary is pointing towards methanol. So it will go towards that vertex. Pause, think, do for yourself. Next, take one more point. Again, towards 53.6 if you want. Now it will go towards 53.6, but if you are on the other side of 53.6, it will go along the binary system axis, along the binary side, and then go towards methanol. From methanol, it cannot turn down because the residue curve is pointing towards methanol. Okay, so pause, think, and do for yourself. So now we can identify that there will be several distillation boundaries. Can you identify the distillation boundary? There'll be a one distillation boundary like this. There'll be one distillation boundary like this. There'll be another distillation boundary like this. And correspondingly, we will have three distillation regions. One distillation region like this, the residue curves in this region will remain in this region. Another distillation region, the residue curves in this region will remain in this region. And a third distillation region like this. So that's how you would generate an approximate residue curve map. Pause, go back and forth in this part of the video and make sure that you have understood this, because we are going to use these residue curve maps now for doing azeotropic distillation. Okay, this is how the distillation boundaries will look like. Okay. Here is a practice problem for you. Now, these I'm not going to tell you the components. I'm just going to say L, lowermost volatile L, the next volatile intermediate I, and the next this volatile H, low boiling, intermediate, and high boiling, 90, 110, and 120. They all form minimum boiling azeotropes, or sorry, I should not say minimum boiling for azeotropes. They form azeotropes. So azeotrope between L and I is 115. Is it a minimum boiling or a maximum boiling? Right, it's a maximum boiling, because the boiling temperature is 115, higher than 90 and 110. Next, between I and H, binary, azeotrope at 105, is it a minimum or a maximum boiling azeotrope? Right, minimum. Okay, binary between L and H, 90, 120 are the individual components, 80 is the azeotrope temperature. Is minimum boiling or maximum boiling? Okay, right, minimum boiling. Okay, now the ternary azeotrope is at 100 degrees centigrade. Is it a minimum boiling, maximum boiling? Well, we can't say, because the boiling temperature is higher than L but lower than I and H. So we don't have to say minimum boiling or maximum boiling. It is just a ternary azeotrope. We don't have to call it by anything. Okay, order of volatility now. What is the order of volatility? Right, points 1, 2, 3, 4, 5, 6, 7. Again, there are three pure components, three binary azeotropes, and one ternary azeotrope. 7 points are there. Write the points 1, 2, 3, 4, 5, 6, 7 in the order of volatility, means highest to lowest, and means the lowest temperature to highest temperature. So most volatile, let's call this point number 1. Next 2. Next 3. Next 4. Next 5, 6, and 7. Okay. Identify the binary azeotropes and draw the residue curves on the sides of that triangle. Okay, so which side? Let's take the horizontal axis. Binary between I and H. It's a minimum boiling azeotrope. Residue curves will point away from the azeotrope. Binary between L and H. It's a minimum boiling azeotrope. Residue curve will point away from the binary azeotrope. Binary between L and I, maximum boiling azeotrope. Residue curves will point towards now take different points along or around this minimum point and try to draw lines. The direction of the line should be how the temperatures would increase, all volatile, less and less volatile, so temperature would increase. Pause and do it for yourself. Pause, pause, pause and do it for yourself. Okay, so if I take point somewhere here, let's say it will go towards 90 along the side of the triangle, then it will turn towards 115. But from 115, will it end at 115? Is that the highest temperature, or is it ending there? No, the highest temperature is 120, so it will go towards this 120. So if I'm somewhere here, as your binary residue curves will go like this. If I'm on this side, it will go like this. If I'm here, it will go like this. Do you agree? Pause, stop, and understand for yourself. Pause. Now we have exhausted all points around 80. We still have covered only a small part of the triangle. Take the next volatile, that is 90. If I take points around here, there's nothing different about them. Here, just goes here, just goes here. So we have exhausted this point. We have exhausted this point. Take the next most volatile point, 100. So now take points around this 100. So if I take this point somewhere here, if I take the point here, oops, if I take the point here, it will go in this direction. It will go from 100 to 105. If you are on the left side of 105, where it will go to? Residue curve is turning and taking towards 110. Will it end there? No, residue curve is pointing towards 115. It will go towards 115. From 115, is it going to end at 115? No, that's not the highest temperature. Highest temperature is 120. It will go and end here. If I'm on the other side, say somewhere here, we are in this direction, it will go towards 105 and then end at 120. So if I'm somewhere here, it will go like this. Now can you identify how many distillation boundaries are there? Yes, there's only one boundary, like this. Anything on the lower side of this distillation boundary will be in this part. Anything on the upper side of this distillation boundary, you will be in this part. Okay, pause, do it for yourself. If you have doubts, you can always go back and forth in this lecture. That's the advantage of a recorded lecture, that you can always go back and forth, 5 minutes back, 10 minutes back, and start and go forward. Just drawing the steps again. I'm just telling you the steps again. Identify the binaries, draw the residue curves on the binary, then start from the lowest temperature and try to see how the residue curves will look like. You go from the lowest temperature in the order of increasing temperature. Take different points and see in which direction is your curve going to take you. Okay, now this is the azeotrope ternary, this is the residue curve map for we had seen for acetone, chloroform and methanol. Okay, now you should be able to draw this yourself. Okay, so this part of the lecture is very short lecture, but it's a very important concept wise. We have seen how to generate an approximate residue curve, approximate residue curve map, and it's very important that you understand this part of the lecture. So I'm keeping this lecture very small. Try to understand how do I generate an approximate residue curve map. Okay. Once we do that, then we will go forward into using these residue curve maps for doing distillation, trying to purify components using azeotropic distillation.